So 12-2 permutations and combinations, I'm going to focus a lot more on permutations than combinations. And I do have to say that this section is about counting again. We're not quite to probability yet. Let me explain why we're not ready for probability. Okay? We're not ready for probability because there are certain things we don't know how to count yet. For example, if I told you that there were 52 cards in a deck, standard playing cards, standard deck of playing cards, and let's say we were playing a game, and I gave everybody in the game 4 cards, okay? So 4 cards dealt out. And you were really hoping to get the following cards. You're really hoping to get the Ace of Hearts, the Ace of Diamonds, the Ace of Clubs, and the Ace of Spades. Well, good luck with that. This is a probability problem. You're hoping to get one specific arrangement. But if you don't know how many arrangements there are total, you can't do the probability problem. The best we know on this problem with our current knowledge is that there is one desired arrangement out of many. See? But if we don't know how many, then we certainly can't do probability yet. See? So this book does a nice job with probability because it refuses to teach you any probability until you can count everything perfectly. And then it says, okay, let's talk about possibilities. Okay? So how many is the question? You can't find the denominator, you can't do the problem. Sometimes the numerator is fairly challenging to find. It's not always one, you know. Okay, question, and then we'll move on.
Oh no, I was just going to ask you, is the probability 1.53908 times 10 to the negative 7?
Possibly, I don't know. Okay, let me just say, this problem you probably could handle actually, because technically to get 4 cards from a deck of 52, you could use 52C4. There are that many. There are 52C4 4-card hands in a deck. Okay. So one of them is desirable, the others are not. So technically this is just 52C4. You see. 52C4 is a huge number. It represents the number of 4-card hands that exist, and one of them is desirable, all the others are not, see? So here are the numerators. Real simple. The bottom takes some thinking. Thank you. It's one, turns out it's 1 in 270,000 or so. Yeah, it's really hard to get 4 aces, isn't it? 1 in a quarter million chances there. Sometimes the numerator is hard to figure out. Sometimes the numerator is complicated. Like I might say, what if you were able to settle for the 4 kings? You know? Or what if all you really cared about was 3 of a kind? Well, there's tons of ways to get 3 of a kind. So the numerator suddenly becomes more complex. But it's all about counting, right? About using the NCRs in the right times and getting the right values to put top and bottom. So we're just not there yet. Okay? The other thing we haven't talked about at all is arrangement. Okay? Let's say that you not only wanted to get these cards in your hand when I deal the cards, but you wanted to get them in that order. Now, do you think that would be easier or harder to accomplish? Harder. That would be really hard to accomplish. It's already practically impossible to get the cards. And now you want them to come into your hand in this order? Ta-da! How's that going to happen, right? That's really, really slim chances to get them in that order as they're being dealt, you see? We haven't talked anything about order at all. We haven't discussed that. So we can't count how many orders there are, although we feel like we could probably count how many 4-card hands there are. We haven't talked about the order of the cards on it. So until we do that, we're not ready for probability. So sorry, probability fans, you're going to have to wait one more day. Okay? All right. So I actually want to jump into order now because it's pretty easy to teach. Actually, I think I'll do one more 2-part problem that involves combinations where you count, and then we'll do order from there. So I changed my mind. All right. So my example is, I don't know if you've heard, there's this new restaurant in town called Shoreway. They make sandwiches. They make Subway sandwiches. Have you guys seen it? Okay. Shoreway sells sandwiches. And they have 5 types of bread. Three types of meat. I'm a cheapskate. 4 types of cheese. And Swiss cheese is there, by the way, because Subway stopped offering it. So Shoreway definitely has the Swiss cheese. It's the last I checked. So I don't go there anymore. Just kidding, I still go there. 3 types of meat, 4 types of cheese. Let's do 10 types of vegetables. And 2 sauces. How many sandwiches can be made if one of each item is picked? So you probably can tell by the fact that I only have 3 types of meat that I'm already a cheapskate here. I'm not going to go buy the good stuff. Okay? It's expensive for my business, so I bought the cheap meats, bologna, pressed ham, and I don't know, something else cheap. Okay? Pastrami. I don't know, is that cheap? So anyway, we've got only 3 types of meat. What you don't realize is why you're only picking one item. I'm really a cheapskate. You're only allowed to pick 1 vegetable for your sandwich. Okay? And only 1 sauce. Okay? And so 1 type of bread, of course. That's normal. That doesn't make me a cheapskate. So anyway, everyone understands the real reason I'm enforcing this rule that your sandwich can only have 1 meat, 1 cheese, and 1 sauce, and 1 vegetable is because otherwise I can't teach you the basic principles of counting from this example. So I have this ridiculous rule that you can only pick 1 of each. So it's probably not going to be the greatest sandwich in the world, and you're probably not going to come back to my restaurant. All right? But how many sandwiches if only 1 item per category can be chosen? What's the answer to this problem? Do you guys know? Yeah, 1,200. So how did you get that? Yeah, 5 types of bread times 3 types of meat times 4 types of cheese times 10 types of vegetables times 2 types of sauces, 1,200 sandwiches. Okay, so you might argue with this problem and say, well, that's not fair, Mr. Shore. I hate vegetables. Don't make me put a vegetable on my sandwich. Well, if we don't make you take the vegetable, then that just changes the problem a bit, right? Some people do like vegetables, some people don't like vegetables, some people want all the vegetables, some people want no vegetables. That just opens up a huge can of worms, right? So we're not going to discuss it in this problem. In this problem, the rules are specific. You can only pick 1 of each item, and you have to pick 1 of each item. So maybe that's a ridiculous rule. If you didn't have to pick a vegetable, that leaves open an 11th option of no veggie. Is that what you're saying? Yeah, we can sometimes think that way. So now there's 11 types of vegetables, including the no vegetable category. Yeah. So this question doesn't get into that. It's not that specific. But this has a name. This is called the multiplication principle of counting. We counted by multiplying. So this is called the multiplication principle counting. Or I will refer to it as MPOC because this is the most basic counting principle we can think of. Count up multiple ways by multiplying instead of adding. Okay? If you're not sure why this rule is working, let me draw a little picture for you. So you walked into the store. There's exactly 1 Shoreway at this time. We're hoping to expand. So that little dot means there's 1 Shoreway restaurant in the whole world. What do you suppose these 5 lines represent? the 5 types of bread. There are 5 types of bread. Okay? Now, for each of the types of bread you pick, there are 3 possible routes you could go when it comes to meat, right? So you could pick, sourdough, that's 1 of 5. And then you could pick your pressed ham, your pastrami, or your bologna, right? So each of these 5 nodes then branches off into 3 possible parallel universes, So now we're counting meats, see? So this branches off into 3 possibilities. And this into 3 possibilities. And each of these 5 nodes has 3 possibilities, Okay, so this is your meats, right? There are 3 meats. So each of the 5 nodes produced 3 nodes. So naturally there are 15 nodes here, right? 15 different locations. They represent, possible configurations of 5 threads and 3 meats. And you can see what's going to happen next. Each of those 15 nodes will then split into 4 more. So now we're up to 60 nodes. And then each of those 60 nodes is going to split into 10 more when you hit the vegetable category. Now you're up to 600. And lastly, you get to the very end, you've got your bread, you've got your cheese, you've got your meat, you've got your vegetables, and they say, which sauce do you want? There are 600 sandwiches and possible so far, and you can choose either sauce A or sauce B. That doubles your options of sandwiches. So it's clear to see why this is working. I can't draw the whole picture because there'd be 1,200 nodes, and it would take me a long time. And I don't want to do that right now. Okay, but do you see why it's working? Okay. All right. Let's go to this next example. Question? Comment?
Are those, numbered out on the shoreway? The front door?
On the front? Yeah. Actually, to get your sandwich, the last thing you have to do after you pay is you have to tell me how many possibilities there were. Then you can get your sandwich. If you can't answer that question, I charge you, and then I keep the sandwich. All right. You like that? Okay. It's pretty dishonest, actually. I wouldn't really do that, just being ridiculous. So let's talk about bus routes to work or commuting, that sort of thing. So when I was a kid, you guys want to hear a little story? Of course you do. So when I was a kid, there were several ways for me to get to school. My parents always lived at least 45 minutes from school. I was in Taiwan, and living near my school wasn't an option. So one morning, my dad would say, you guys have the car today, so we drive to school. That was nice. Some days he would drive us there and drop us off, and then we had to figure out how to get home. There were many ways. But then some mornings he would drive us to the train station in our little farm village, and then we would take the train to a town outside of a town that's outside of my school's town. And then we'd take a bus from there to the next town, and then we'd take a taxi to school. So that was like an hour and 15 minutes of traveling. It was train, bus, taxi. If we had a little more cash at that time, we'd skip the bus leg and just do taxi all the way after the train. But it was always kind of a mess to get to school. It's just the story of my life. Even in college, I commuted. So lots of commuting for me. So anyway, this problem is kind of about that scenario. Let's say that a person has 3 bus routes they could take to work. So 3 bus routes they could take to work. Or 4 roads they could drive on to work if they have their car. 4 roads they could drive on to work. If they decide to drive, okay? So there's a couple reasons why someone might not drive. Maybe they're just, the car isn't very reliable. They can wake up on some mornings and realize that car's not going anywhere today, so they take the bus. Okay? Or maybe this is one of those people who really, really, really cares about the environment, so they won't drive. So they get in the bus and let the bus pollute the environment, and they feel good about themselves for some reason. Okay? So, anyway. 3 bus routes they could take to work, or 4 roads they could drive on to work if they drive that day. Okay, so the question is, how many ways are there to get to work? So for this one, you might want to draw a picture. Here's home, here's work. There's bus route A, B, and C. And then here are the roads, 1, 2, 3, 4. So the 3 blue lines just represent bus routes, and the 4 green lines represent driving routes. But it's clear to see that we would not be multiplying the 3 and the 4 here. Right? There are obviously 7 routes to work. So why is it that in this problem we are adding 3 and 4, but on the previous problem we multiplied 3 and 4? You guys understand the question? When do you multiply? When do you add? So can you tell me, Jace, why do you think it is that we're adding here?
Okay, well, on this one, it's just,
Nice and loud.
it's just 7 routes that you can choose from, whereas on the other one, you choose 1 of 5 and then have to choose between 1 and 3 again. So
Okay.
you have multiple decisions.
Okay. So you have multiple decisions to make on the Shoreway sandwich one. Here you only have one decision to make. That's a good point, actually. Jack?
Oh, that's just that, it's like an or and and kind of thing. You can take 1 of 3 bus routes, or 1 of 4 driving routes.
Yes.
Versus the other one, you can pick 1 meat and 1 sauce and 1 vegetable and 1 bread.
Okay.
On and
Yeah.
on.
Okay, so what were you going to say, Blake?
I would say the and or.
Yeah, there's a definite difference between the structure of the situation, right? I like both answers you guys gave. One is just simply that in the first situation, you were forced to make multiple decisions. You had to accomplish more than one task, and you had to accomplish all those tasks. So you have to multiply your possibilities together, right? Whereas on this one, you cannot possibly achieve both. You can't drive to school and take a bus to school or work. I mean, that just isn't possible. I don't know, I guess it doesn't make sense to do both, you know? So multiplying them would imply you're wishing to do both, but that's not possible. So you would add them instead. But you're right about the or. The or is implied here in this, it's not stated, but it's definitely an or. Look, you ride to school or you drive to school. You know, you ride to work, you drive to work. It's one or the other. So that's when you add. Okay? So now let's talk about situations like that. So let's say Mr. Shore wants to get a new skateboard. So I go into the store, and I'm going to choose a deck. That's the wood, right? A grip tape. They have so many options. Some of them are really lame. They glue on your shoes, and they wear off. Who wants that? You need to probably pick trucks. That's the wheels of the board. You know, you need to pick your wheels. So depending on the hardness and the size, pick your bearings. Do you want the real gimmicky ones that say ABEC 10, which is not even true? Or do you just want the standard ones a little cheaper? Are you gonna, you got to pick hardware, right? You got to put the bolts in. They've got Allen head bolts. They've got Phillips head bolts. They've got the colored bolts, you know? So this is one of those situations where you're not walking out of the store until you build the whole board, right? So is that a case where you multiply your options or add? You multiply, right? Because you have to buy every one of those things and then assemble it. So this creates a whole slew of possible skateboards, right? Or if you're building a Mini Cooper, I think there's 21 million ways to do it. You can check the website. It says on there. It's just multiplication principle of counting. Okay. Build your own Cooper online, yeah. Yeah, and it tells you how many options there are. So, you know, with stereo, without stereo, that kind of thing. All right. What if the question was more like, hey, tonight my wife is, 3 possible meals and 3 possible desserts. Would I multiply 3 and 3 to figure out the number of dessert meal combos, or would I add them? We assume that I'd probably eat dessert and dinner, right? So probably both, and then multiply. Whereas if it was like, hey, my wife says, hey, we can do, one of these 3 pastas tonight, or we can do, one of these 3 casserole dishes. What do you want? Well, that's 3 plus 3. There's only one meal here. See, so you add your options together. Does that make sense? This is the main question people have about probability also. When do you multiply, when do you add? It's almost always the main question people ask. Okay? So it's actually pretty easy to answer. It's all depending on how many decisions you have to make. Each decision is one number, and then you multiply them if you have to make more than one decision. Okay, we'll see that again in probability too. All right, so everyone sees there. What about this one? Shore's class has, how many boys did we say we had yesterday? 14 boys, that's right.
No, 12.
It was 14 girls, I remember. So it's 12 boys and 14 girls. If Mr. Shore wants to form a committee of 3 girls and 2 boys, how many committees are possible? So before you get all up in arms about this and say, hey, the committee is imbalanced, you've got 3 girls and 2 boys. Well, you have more girls and boys in the classroom. So it's kind of like, you have a state with a lot of people in it, they get more representatives in the government than the smaller states, right? So in a way, it's kind of equitable, if not exactly uniform. It's still equitable, or you could say it's not. I don't know. Depends on your political views. But my point is, I wanted to form this committee. For one reason or another, it has 3 boys and 2 girls. So how would you form this committee? Like, how many ways can that be done? Well, you can kind of think of it as Mr. Shore is going to have to actually do this, right? He's going to actually have to have a list of girls' names to choose from. So imagine putting those in a hat. 14 girls' names. I'm going to pull out 3. And then another hat, with 12 boys' names. I'm going to pull out 2. So you already know how to pull 3 from 14. We've been doing that. How do you pull 3 from 14? Like, how many possible ways are there? We call that 14C3, right? This is how many ways to choose 3 from 14. How many ways are there to choose 2 from 12? We call that what? 12C2. Now, does Mr. Shore want a committee with boys or girls? Or does he want a committee with boys and girls? He wants a committee with boys and girls, right? I'm trying to get some kind of equitable representation here. So it's not like I can make one decision. I need to make 2 decisions. So what am I going to do with these 2 numbers? I have to multiply. I don't have a choice. Okay? Now don't tell period 2 or 3 that this is a multiplication situation. I asked them to think about it tonight. But since this is my only video for 12.2, I thought I'd put the solution in. Okay? They're thinking about this one tonight. Are they going to add these or multiply them? The answer is you'd multiply. I need the committee to have both boys and girls. See? So this is a calculator problem, probably. But can someone get us that answer?
24,024.
So 24024? Yeah, these are possible committees. That's kind of surprising, but there are over 24,000 committees we could create right here in this room. Isn't that crazy? Hard to imagine, right? Now, of course, there's some people who aren't interested in being on a committee, so they might opt out, And whenever human will is involved, it changes probability. That's why you need random sample sizes, and you need to interview random samples. You can't just go online and say, I'm going to try to see how good my calculus teaching is, and then basically put up a Mr. Shore's class rocks, Mr. Shore's class doesn't rock poll on Edmodo, and then the kids click on one or the other. That doesn't work at all, because only people who are interested in expressing their opinion are going to get on there and do that. The others who don't really have an opinion, maybe they're just kind of cool with everything, easygoing, or maybe they're bitter and angry and don't feel like expressing that. To bottom it up, whatever. They're not going to say anything. So I get this data, and it looks good for me or looks bad for me, but it doesn't mean anything because the sample set has been biased. Only the techie people or the opinionated people or the outspoken people are going to vote there, see? So it's just a bad experiment, as you'll find in Miss Petrella's class next year if you take it. Certain experiments are worthless. That is a worthless thing for me to do. I guess I could force everybody to answer, but then
So then
they could lie.
You just also bias the group if they're mad you made the
Yeah.
answer.
Now they're mad at me for making them do something on Emoto, you know? So, you guys see the point there? I have no idea how that came up, but it's an important point in statistics to be careful about. So, all right, let's talk about cards again. Let's go back to cards. Okay. How many cards in a standard deck? 52. So there are 52 cards, and they're distinct, right? You won't find 2 ace of spades in there. If you see 2 ace of spades in your deck, something's fishy or it's a pinochle deck. Someone's cheating or it's a pinochle deck. That's pretty much the only 2 possibilities there. So 52 distinct cards. I know not everyone plays cards, and I'm not endorsing card playing. I'm just saying it's a very standard thing to do with probability is to discuss card arrangements. So there are 52 distinct cards in a standard deck. We need to talk about shuffles, okay? Shuffling. So I heard that if you shuffle, like if you break it into 26 and 26, and you shuffle every other card, like if you can fan it, if you can get a perfect Faro shuffle, it's called, and you can get every card to stack one on top of the other, one after the other perfectly, and you do it 8 times, it goes back to the original arrangement, or 4 times. I can't remember. The point is, nobody shuffles that well unless you're a pro, and but you can actually shuffle enough times to bring it back to the original arrangement. So that's a pretty nifty little trick. But 52 distinct cards in a deck. How many total shuffles are there? You know, you play 52 card pickup, right? You throw them in the air, and then let's say you close your eyes and put them all into a pile. Well, that's one possible arrangement, right? Then you throw them in the air again, and you close your eyes and gather them all into a pile. Well, there's another possible arrangement. How many possible arrangements are there? So how many total shuffles? How many total shuffles are there? Well, 52 factorial is the answer. See, the ace of spades has 52 possible locations, but the ace of clubs only has 51, because the ace of spades has already taken a spot. And then the ace of hearts only has 50 spots, because the other 2 aces already stole a spot. See? And so this opens up one of those little node drawings where it goes 52 options and 51 options. It's actually diminishing. So this is pretty easy. Most people know this. If there are 52 objects, there's 52 factorial ways to arrange them all. Okay? Okay. That's the first question. How many 5-card hands can be dealt? So for those who don't play cards, a 5-card hand means you were given 5 cards to hold in your hand. 1 for each finger, I guess. Okay? So in this particular game, I'm just asking how many different possible hands exist. So this would be a question of choosing 5 from 52. Simple. So you would just do 52, choose 5 cards. You could do this by hand, or use your calculator. Where does the 47 come from? Remember, it's first number factorial over second number factorial, and also on the bottom, the difference factorial, right? Okay, so you can do that. This is obviously not as big as 52 factorial because you're dividing, but it's a big number.
It's 2.59,896 times 10 to the 6.
Okay. So give me those first 4 sig figs again.
2.598.
Actually, does anyone have a TI-84? Or does anyone have the whole number? 960. So there's about 2.6 million different possible sets of 5 that exist in a deck of cards. It's kind of hard to believe. This means you might have the ace, the 4 aces, and then the king of clubs. That's one arrangement. Or the 4 aces and the king of hearts. That's a different arrangement. Or maybe you have an ace, 2, 3, 4, 5, and they're all hearts. That's an arrangement, right? So if you're super picky and you're like, I need the 4 aces and the king of clubs, please, 2.6 million chance of getting it. Good luck with that. Okay, makes you not want to gamble, right? All right. How many ways are there to arrange 5 cards in your hand? Now, some people, when they get their hand of cards, they seek then to shuffle them into fun arrangements. How many of you, after you get your cards in your hand, whether you're playing Uno or whatever, you start to organize them? Anyone start to organize their cards? Don't you hate it when you have like 12 cards and you're like falling out? You're like, not supposed to see that, right?
You're just like, just put them out. Just
Yeah, if you're good at fanning them out, that's cool. It looks cool. You cool yourself off. See, he's got cards. So, the question is a little more complicated now, right? You're not only planning to get 5 cards, which already has 2.6 million options, but then you're picky enough to want to arrange them, you see. So we can actually use part B to kind of get to our answer. First, we got to get the cards. Right? And then we have to arrange them. Arrange the 5 cards. Okay, so let's draw a little picture here. Let's say these are your 5 cards. And just for the sake of argument, let's call them cards A, B, C, D, E. And then here's your hand. Don't laugh. That's a really small ring finger. That's just weird. Okay? And you're planning on putting them into your hand, kind of one for each finger sort of thing. How many ways are there to put them into the hand? If they're already on the table, you're picking them up, now you're going to arrange them. Well, how many ways are there to do that? How many choices do I have when I place a card by my thumb? 5. How many when I place the next card at my forefinger? 4. How many choices do I have when I pick one to put near my middle finger? 3. How many when I choose one near my ring finger? 2. And the last card, well, I guess just has to go here. Now, is this something I want to do all 5 of these things? Or do I wish to just do maybe one of these 5 things? I'm planning on taking the 5 cards off the table, picking at them, and then arranging them. I'm going to do that by placing one next to each finger, in my hand. Do I want to place all of them, or some of them, or one of them, or what am I trying to do here? I'm going to do them all, right? So I'm going to multiply these. 5 times 4 times 3 times 2 times 1 tells me how many ways there are to go from there to there. How many ways are there to shuffle A, B, C, D, and E? There are 120 ways to organize A, B, C, D, and E. Okay? Okay, so this gets multiplied. So there are another 5 factorial arrangements. That's 120. You don't really need a calculator for that. Okay, so let me ask you this. What am I going to do with the 2.6 million and the 120? Do I wish to collect the cards or arrange the cards? Or do I wish to collect the cards and arrange the cards? I wish to collect the cards and arrange the cards. So am I adding these or multiplying these? Multiplying these. So now I need to multiply 2, 5, 9, 8, 9, 60 times 120. And that's getting really big. What is that?
311,875.
Right. So let's say that you really were hoping to get those 4 aces and the king of clubs. You have 1 in 2.6 million chance. Probably not going to happen. Let's say you really were hoping to get them in this order. Ace of clubs, ace of hearts, ace of diamonds, ace of spades, king of clubs. Like the dealer had to give it to you in that order. No way. That's impossible. You got it right there, look at that. 1 out of 1 probability. You brought his cards to the IC. But you can see that now your chances, because you're so picky, you want them all in the right order, now your chances are 1 in, a third of a million. So, no, 1 in a third of a billion. So your chances are getting slimmer because you're being more picky, you see. Okay. So this is the number of ways to pick up 5 cards and then arrange them in your hand. Okay? Okay, so let's look at that problem a little bit faster next time. We shouldn't have to do all that work. What does 52 factorial over 5 factorial 47 factorial measure? What does that measure? Number of ways to get, right, 5 cards from 52. Right? What did the 5 factorial mean? Number of ways, what? To arrange the cards into your hand, right? To arrange them in your hand. Do you notice that something cancels here?
Yes.
What cancels here?
5 factorial.
The 5 factorial. What does that mean? It means that when you want to take 5 from 52 and arrange them, you don't need to do a combinatorial formula and then multiply by r factorial. You don't need to do n factorial over r factorial times n minus r factorial times r factorial. The r factorial is going to cancel. What you really need is a new formula for this that looks like, if this is n and this is r and this is n minus r and this is r, the r factorial is going to cancel anyway. You need a new formula that just looks like this, n factorial over n minus r factorial. And this is the NPR formula. Okay? So brand new rule, NPR is n factorial over n minus r factorial. What's his job? He counts shuffles. You take some of the elements in a group and you arrange them. That's his job. He'll tell you how many shuffles there are. And the perfect example is, hey, take 5 cards from 52 and arrange them in your hand. 52 p 5 will give you the number of arrangements. And it includes the number of combos, too. That's why the number is so big. Okay, so let's look at the formulas we've come up with so far. You know I'm storytelling all this. I could have just given you the formulas at the beginning of the lesson. The first thing we learned is that this formula here has a job. It tallies the number of ways to select R elements from a set of n distinct elements. Actually, it doesn't have to be distinct, just elements. Okay? That's his job. Don't use it for anything else. We also saw that some people like to write it this way. So AKA that thing. And you can also find these in Pascal's triangle, which is kind of cool. Okay. In PR is totally different. It's n factorial over n minus r factorial. It doesn't have that extra ingredient on the bottom. And the job here is to find number of ways to select and shuffle R elements from a set of n elements. And believe it or not, there's another formula that we've already learned, and it's this one, n factorial. N factorial is the number of ways to shuffle all the elements in a set. With n elements. So for example, if all you wish to do is shuffle your cards, there are 52 factorial ways to do that. If you're holding 5 cards, there's 5 factorial ways to arrange them in your hand. This leaves us with one last question. What do we do if we are given duplicate objects and asked to shuffle? Okay? Now this would never happen with a deck of cards. I told you there's only one ace of clubs in a deck of cards. Something's fishy if you find 2 of them. One of them was probably up somebody's sleeve a moment ago. Okay? But this can happen in other situations. Okay, for example, let's say that I gave you this word here, Mississippi. And I said, okay, I'd like you to go ahead and rearrange the letters. I'll close my eyes, you rearrange the letters. So I close my eyes, and you switch the two P's around. And I open my eyes, and I look at it. And you say, well, I made a new word. I'm like, it's the same word you had a minute ago. Well, you'd say, nuh-uh, I switched the two P's when you weren't looking. Okay. Did you really create a new word? Not really. So there are 11 letters here. Is it safe to say that there's 11 factorial arrangements here? I don't think that's very fair to say that there's an 11 factorial arrangements here. Because many of those arrangements are just duplicates of something you already have. Like when you switch the two P's around, I would hardly call that a new arrangement. You see? So this needs to be divided by something. Does anybody remember from Algebra 1 class, what would we divide by? I mean Algebra 2. Okay, I see two P's, so I do need to divide by a 2 factorial. What else? What else is sort of duplicate or triplicate here? We got 4 S's, right? The 4 S's, you've got to divide by 4 factorial. Because there are 24 equivalent words with just S's shuffled around. Okay, so that needs to be divided off to prevent extra counting. We also have a bunch of I's, don't we? How many I's do we have? 4, right? So there are not 11 factorial. That has been diminished by a 2 factorial, a 4 factorial, and a 4 factorial. So this is the 2 P's. This is because of the 4 S's. And this is because of the 4 I's, you see. So this number isn't as big as you might first think. It's still big. What is the answer here?
831,600. Oh, wait, no, oops.
It doesn't sound quite like the number I heard last period.
Divide by the other 4 factorial.
Divide by 24 then. Make sure you use parentheses, or just do the bottom separate, 2 times 24 times 24. Does anyone have that number? 34,650 sounds right. These are different arrangements of Mississippi. Don't count the extras, right? Okay, I'll send you the lesson. I'll send you the homework assignment through Edmodo. But those are your formulas. I call the last one the Mississippi formula.